Yesterday, you know what I mean, when we were here last, 2 days ago, on Monday, we talked a lot about how do you count significant figures, and the stuff you handed in to me has you counting significant figures. And actually we're going to use that, but not right away. This, if you want to title it How to Round Numbers, you can. How to Round Calculated Numbers, that's kind of what this section is. It's not very long, but how to round. And it's kind of, I said, thou shalt not lie. And when I say thou shalt not lie, I mean you're going to truncate or round at the correct spot according to the numbers that you used in your calculations. Okay. So they fall into two categories. How you round falls into one of two categories. So just to emphasize a few things on this slide. This is the category where the math that you're applying is either adding and or subtracting. If that's what you're doing on your calculator or in your head, if you're adding or subtracting. Now, these things, and I'll get really quiet like kindergarten teachers do, because this is very, very important. This little section on how to round is something that's going to apply for the next, 14 weeks? How many weeks we got? So how you round is actually going to be applied to all the things that you hand in. That includes your exams, plus, who cares, your homework. You know, keep doing your homework and I'll grade it. But your exams are really where the points are. You have to round correctly. If there's something that's worth like 15 points on a test, you do it perfectly, you show your work, that's another thing. You show your work, you do it perfectly, you get the right answer, but you round incorrectly, you will not get the full credit for it, because that's how big of a deal it is. All right. So if what you're doing on your calculator in your head is adding or subtracting, what you do is you're going to round, but it's not according to the significant figures that we spent so much time on Monday. Okay? You're going to round according to what we call the fewest number of decimals, or tens places if your number's large. So you're literally going to count decimals. You're going to count decimals. Let's just try that. Okay? For kicks, what if I put 7.930? Okay, how many decimals are there? 3? Exactly. And actually, I'll even go ahead and use check marks, kind of like I used for sig figs. Though we have 3 decimals. That's what I mean. Let's put another number. How about 752.1? How many decimals are there? 1. That's all it is. Okay. I'm going to show you why this is, but just for kicks, if you were to put that in your calculator, okay, your calculator would give you back, well, that's not too hard to do in my head. Well, I can't do it in my head. I meant to bring some calculators. I'll just go ahead and show you. Anyone want to borrow a calculator again? Go ahead and get your calculators out. You'll need them. And I'm going to let somebody else, thank you, somebody else do somebody go ahead and tell me what your calculator says. Well, hopefully it's not speaking to you. That's a whole other issue. But what does and a lot of times I'll put CALC for what your calculator displays. I'm ready.
760.03.
One time.
760.03.
760.03. Thank you. Okay, very good. Awesome.
I'm sorry, I missed what you added.
You just add these. I'm just adding.
Okay,
Yeah.
I'm sorry, I missed that.
You're fine. Yeah. Do it. Oh, what are you supposed to do? Yeah, I wanted you to add those 2 numbers. Awesome. That's what your calculator displays. And according to this rule, what this paragraph says is we are going to round according to the fewest number of decimals. Which is the fewest number of decimals? 3 or 1? 1, exactly. So we'll talk more about this and why this is, but basically I wanted to kind of start off the bat that we are going to truncate, we are going to round right there. We're going to keep that because we only have 1 decimal there. That's it. And subtraction would be the same thing. Your calculator displays something, but you have to apply, and I'll tell you how the uncertainty propagates when you're adding, how the uncertainty propagated through this problem. Okay, so we need to go ahead and round according to that. So did you guys learn this, that if you're going to truncate a number right here in the tenths place, we look at the next number. And since this is a 3, do we leave this the same or raise it up to a 1?
Leave it the same.
We leave it the same. It's sometimes called rounding down, which is kind of a strange thing.
So it'd be just 760.
So let me finish this, and then you can,
Sorry.
that's okay. Okay, so a lot of times I will, instead of calc, I will say ANS. Okay, that means answer, rounded to what we're supposed to do. And so we start from left to right, taking digits. So we'll go 760.0. We talked about if like you have something that is weighing mass in pounds. And you say that I have an object that weighs 760.0 pounds. That is a different weighing device than if you say I have an object that weighs 760.0000 pounds. Those trailing zeros after the decimal are telling you something about your weighing device. Okay, so I kind of got ahead of myself a little bit. And actually, speaking of getting ahead of myself, if you look after the kind of the problem where we're going to actually do some addition of numbers, you see this rounding off slide. And this is what you just told me a minute ago. Since I wanted to round at the tenths places and the next digit was a 3, you told me, hey, okay, leave that number, which was a 0, leave it alone. Okay, if that number had been a 5 or greater, what would we have done with that 0? Round it up. Okay? Yes. Round it from 0 to 1. All right. So this is where I'm going to show you just adding. You guys did this a minute ago. But we're adding 2 volumes, milliliters, to different measuring devices because we can see it kind of has different numbers of precision and accuracy kind of at the tail end there. Okay? So we have these 2 volumes. If you read your problem, it says we're supposed to add it together. One of the things about problems, I don't know whether to call them story problems or just problems, is sometimes we go, oh, I don't like words and problems. Okay, but just read them a few times. And we're going to add these 2 volumes together. So one of the things we talked about Monday is that both of those volumes have wiggle room. They have uncertainty, but the person who reported them, we have to assume, did it correctly. And basically, the hot number, the question mark number, is the last digit. So I kind of used this convention on Monday where kind of the red is we count it, and it's significant. We count it as a significant figure, but that's where the wiggle begins. The plus or minus begins. So we have uncertainty at the, tenths, hundredths, thousandths place for the first volume, and uncertainty in the tenths place for the second volume. So of course, if you're adding, you kind of line up the decimals and bring them down. So one way to kind of think of it is any sort of uncertainty, any sort of redness, okay, any sort of redness in these digits added together propagate, I love that word, propagate or kind of carry on down to this stuff down here. They contaminate it, okay? So contamination begins at the tenths place because of the uncertainty in the tenths place for that second volume. Okay, so you're like, all right, so now I have 2 blue numbers for sure, and I have 3 red hot question mark numbers. And again, it goes back to one of the things I said Monday was you can only have 1 red hot number. Okay, so I'm just trying to explain why. It goes back to the thing I told you a minute ago. You have to round according to the fewest number of decimals, which if you go back to what I said, the top number has how many decimals? 3, exactly. That second volume has how many decimals? 1. So you round according to 1 decimal. This is addition. Subtraction has the same effect. Okay? Okay, so just to kind of make sure we're all in the same ballpark, we're going to round to 1 decimal there. Okay? So the digit after the tenths place, the 1 decimal, is a 4. So we left the 6 the same, didn't we? And we call that rounding down, which is kind of strange. It really used to confuse me a time like, wait, that's what that is. Okay? So we're going to truncate it right here, keep that, and we look at the 4, and, okay. Any questions about that? You're going to get some practice at that. Now, with that said, we do, and maybe you already kind of are familiar with this, but I'll ask it in the form of a question. With regard to adding and subtracting versus in a minute, I'm going to talk about if in math, doing a chemistry problem, you need to multiply or divide. How many people, which of those do you think we do most of? How many people think we do a lot of addition and subtraction? We do some. How many people think we do even more multiplication and division?
Even
Yeah,
more.
we do even more, yeah. So we do both. Okay, rules for multiplying and dividing. If that's what you're doing in your chemistry problem or any sort of physical science problem, if you are multiplying and or dividing anywhere, this almost gets, the hardest problems are when you're doing both types, adding and subtracting, and multiplying and dividing. You're going to get some practice at that. The rules change, and I'll try to explain why that is, but let's just kind of show you that the rules change. You look at the things that maybe you have more than one thing lined up to go ahead and multiply or divide. Okay, you look at all of them. You count significant figures according to those rules we talked about on Monday. Sometimes you'll see in my answer keys, I'll put a little number, I'll put check marks next to digits that are significant, and I'll put a number up that there, okay? You count them. And then whichever term has the fewest, that's how many significant figures you are allowed to keep in your answer. So you're basically going to kind of start from left to right, keeping that number of significant figures. So kind of like we did last time, let's do another kind of a problem down here at the bottom. Let's just say, and I have calculating the area of a rectangle coming up. So let's do something kind of similar with different numbers, okay? Let's say we're after area. How do I get area of that?
Height times the length.
Yep. Length times width or height times whatever. Those two dimensions, exactly.
Same thing. Same
Yes,
difference.
definitely. So let's just say this is 12.3 centimeters. The other one looks shorter. So let's go 9.2 centimeters. Okay, so you told me I'm going to multiply these two together. Let's just kind of get in the habit of showing all of your work, which I will be looking for all of your work. Anything you put in the calculator in lab tomorrow, anything you put in the calculator, write it on your data sheet. Tomorrow's lab, you'll get full credit. I'm just going to kind of be walking around looking at your data sheets. So, and a good way to show multiplication is just to kind of squish them together. So I'm going to put 9.2 centimeters, no naked numbers, times 12.3 centimeters. Yes. And so one of the things that we're going to be talking more about is that, and I'll introduce you to this idea, is do you see where we have a number and a unit and a unit? Basically, the numbers are going to be multiplied times each other, but we can't forget the units. The units are going to carry along too. Okay, so someone tell me, and I'll put the word calc for here, C-A-L-C. Somebody tell me what their calculator displays.
11.96.
It is 11.96. That's what your
Yes.
calculator, thank you. Very good. Okay, so that's the number part. What about the unit part? What's centimeters times centimeters?
Centimeters squared.
Centimeters squared. Centimeters raised to the second power. Questions? Did you get 11.96?
No.
13.16.
Oh, we're going to do it like our calculator. Not like our calculator. We're going to do it kind of like our checkbook. So tell me the alternate one.
113.16.
113.16. Any takers? Okay. Well, you got overruled. See if you can get this. 113.16.
Yep. Now I got that.
Perfect. Okay.
Really good.
This is what we're here for, right? Consensus rules.
Sorry, guys.
You're good. You're good. Appreciate you guys doing this. Okay, so when you take 9.2 and multiply by 12.3, 113.16, do you guys see where the units, like Nina said, would be centimeters raised to the second power? We're going to be doing a little bit of that. All right? Cool. Now, that's what your calculator displays. And to apply this rule, this is how this works. How many significant figures in 9.2? There are 2. Very good. How many significant figures in 12.3?
3.
There are 3. Quite simply, all you need to do is go with the 2. Does that make sense? So to apply two significant figures to this number, and this is a good example, we start from the left and go right. Sometimes I get my left and rights mixed up. So this is to say I am going to keep the digit in the 100ths place. I am going to keep the digit in the tens place. But I have to stop there. So this makes it interesting. Now, before you ask any questions, let me go ahead and just kind of finish this thought. Okay, so I have a 3 here. First off, since that's a 3, what do I do to this 1? I leave it the same. But here's the deal. I am going to have to go ahead and put a 0 there in the 1's place to kind of give the 100s and the 10s place magnitude. So you're right. I'm going to leave that 1 the same. So I'm kind of running out of room here. So let me write my answer, carried on up here, 1, 1, 0 centimeters squared, no naked numbers. That is the right answer. That's the only answer. Two significant figures. We say we're limited by the two significant figures that is in this dimension. Okay, if somebody went ahead and coughed up another sig fig, hey, we'd go for 3. Okay, but it was limited. Any questions about that? Okay. So again, I kind of wanted to cut to the chase. We're going to do an example where you have two dimensions here. One dimension you know to 3 significant figures, right? Oh, one dimension you know to 4 significant figures, 12.34. The other dimension, again, you only know to 2 significant figures. To get area, you multiply those two together. So let's go do it. Okay? So a long time ago, before calculators, I don't know if they still make kids do this or not. But actually, you can do it out longhand. Now, sometimes students, when I say show your work, it takes a little bit for students to know, I don't want to see this work. Okay? I don't need to see you do it longhand. Okay? But again, I use the word propagating, or how the uncertainty kind of flows through your multiplication process. There's uncertainty in both of those measurements, red hot number. Okay? Long time ago, maybe, you learned that if you want to multiply things together, you have to do it this way. Or basically, you take this and multiply it through by these digits. Okay? When you do that, it gives you 1, 2, 3, 4 hot. Right? And then you slide over 1. Okay? And then you take, or 1 column. Okay? And then you take this number, again, times this. And you have it indented. Who thought of this, right? Love powers of 10. And then once they're lined up, you have to, without crossing your eyes, basically kind of bring down the numbers. Whew. And again, I don't need to see this. I'm just trying to show you how, this kind of happens. So notice that if there's any sort of red in adding here, that number is red or uncertain, okay? So we have uncertainty basically from the 1's place on out. How many uncertain digits can we take in our answer? How many red numbers? Just 1, only 1. You can try to take more, but you'd be lying. Scientific community, jump all over you, okay? Okay, so we can only take 1 red number. Okay, so since this, you can already see it in the answer here. Since this is we're going to round here, we're going to cut it off there. We look at the number after the 1 in the 1's position. Okay, so after the 1's position is a 5. So what did we do with the 3? We rounded it up. Yeah, we rounded it up. Any questions? Okay. And again, don't forget your units. Okay. Centimeters times centimeters is centimeters squared. That's it. Okay. It was nice to do that one where we had the 110, with an implied decimal after the 0. Okay, a little bit ago, but that's where it gets kind of tricky. Any questions? All right. Exact numbers do not affect your answer. And I don't have an example in my notes, but here's one for you. What if, let's see, how many do we have in here now? 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 of us. Is 11 an exact number? Yes. We know there's 11. Nope. No students under there. Okay. So what if each one of us had, this would be kind of hard to do, but we could do it. What if each one of us had your cute little graduated cylinders, and you have exactly in your graduated cylinders, let's take your 10 mil graduated cylinders, and let's say you have a volume of 5 point, I'm trying to think of the gradations there. I think this is right. What if you have 5.13 milliliters, each of us? Or 11, did I say? Okay. And we wanted to know what was the volume we'd have if we combined them together. So what would I do there?
Multiply by 11.
Just multiply it by 11 people. Okay? That 11 brings no uncertainty. When I'm multiplying, so my rule is to round according to sig figs, which I will. But you're not going to see me put check marks over my 11 because that's exact. No uncertainty. You're going to see me put check marks over that volume. So how many sig figs do we have in that volume? 3. We do, exactly. Whoops. Okay. We have 3 sig figs. So somebody tell me what the calculator says.
56.43.
How many people got 56.23? Oh, yeah. Okay.
I think I'm waking up finally.
So now I do like the habit of writing 2 things. I like writing what your calculator displays. It kind of keeps it neat and we're all kind of on the same page. It can really actually kind of save your butt if I'm trying to look at what you did and trying to give you partial credit in some cases. Okay, so 3 sig figs, it's always kind of it's always from the left to the right. So we're going to keep the 5, keep the 6, keep the 4, and since the number beyond the 4 is a 3, what are we going to do to the 4? Leave it the same. Are we good with that?
What would it be, milliliters per people?
In this case, I would probably just ignore the people part. 56.4 milliliters total. Any questions? Total volume. Good. All right, we're set for the semester then. Like I said,
Oh, yeah.
honestly, I'm just saying that I'm going to be looking for that. And I don't know why it's hard for us sometimes, okay, but it is. So something to put on your refrigerator, or just to kind of summarize the 2 rules we talked about this morning. Okay, to emphasize the difference, okay, this is adding and subtracting, okay, and this is multiplying and dividing. And actually, I like tomorrow's lab because you're going to do some simple measurements if you've had a chance to look at it. And you're going to be generating your own data, and you're going to be doing calculations with that data. Doing calculations with measured quantities, that's where the rounding comes in, because there's uncertainty in your measured quantities. Okay. Okay, so here is my stab at, this is kind of the slide where I said throughout this next, till the end of the semester, I'm going to be looking for the correct way to round, okay? So there you go. But this also says, and I guess I should kind of qualify this slide a little bit, and we run into it maybe in the next 15 minutes. Sometimes you have a chance, this talks about an intermediate solution. Sometimes there's a time when you do part of it, you do a little calculation, part of your overall calculation. In that case, you kind of have an intermediate answer that needs to be carried through, okay? Your choices are, and this kind of says, go ahead and round when you can, because it's easy to lose sight of how you're supposed to round. I have an idea of how you're supposed to round for multiple steps. And if you don't round at the intermediate values like this says, a lot of times you lose track of how you're supposed to round, okay? But with that said, you get a slightly potentially better and different answer if you use the unrounded intermediate value to carry through. So, I don't know, there's something to be said for both. Okay, so let's take a look at these. Notice on your notes you need to add 50 back. 50, if you had a chance to look at it, is just the rounding part, okay? So let's look at what those look like. If the internet will let me. Okay. So 50 is there. It says round each of these to 3 significant figures. So just get in the habit, it's good practice to go kind of from left to right. You'll take this digit, this digit, this digit. Truncate it. Sometimes students early on kind of struggle with like, well, I'm going to go ahead and truncate it. And then if it's a large number, they don't fill in with the zeros. You have to fill in with the zeros, okay, if it's a large number. Then the next one you're supposed to do is 58, 62, 64. They look like this. Oh, I guess, well, here's 62. 62, and I think 58. Well, 58, 62, and 64, I believe, are all, what are we doing there? What's the type of operation? Adding and subtracting, exactly. You know, I'm really going to be looking for, I think you need to write these down. You need to rewrite the problem, put the equal sign, and put the answer. Because that's what you're going to be doing for your test. If you put it in your calculator, put it on the piece of paper. Okay? And actually, if you put it on the piece of paper, then it's clearer. And you can actually kind of do little check marks if you want to, counting decimals. Then, as you might imagine, we kind of segue into the other type. What's 68 and 66 doing?
Multiplication and division.
Yes.
And
Both multiplication, division, and subtraction. Let's do an example right quick. Let's say you have 3.7, let's see, plus 2, okay, divided by 79. Whew. Are you familiar with the term orders of operation? Okay, orders of operation say, what are you going to do first? What are we going to do first there? We are going to do the addition. Why are we doing the addition first? Because it's inside the parentheses, exactly. That is so obnoxious. Let me go ahead and talking about obnoxious math rules. I'm going to take the parentheses out. I'm going to put 3.7 plus 2 times, or sorry, divided by 79. Now what do we do first? Divide. We divide first. I didn't make these rules. Don't blame me.
So which one do you want us to do, the one with parentheses or without it?
For now, I'm going to skip this other scenario. I like to be generally clear. To me, this is clearer. And actually, if I do it, I might task you with mixing addition with division. Okay, I'm going to go ahead and probably do the latter. So what I would do, and you'll probably see on my answer key if I'm trying to emphasize how to work this, is I would do it stepwise. So what's 3.7 plus 2?
79.
It is 5.7, really. Very good. So 5.7, that's what the calculator says. Okay? How many decimals in 3.7? One decimal. How many decimals in 2?
Exact.
0. No, it's not
It's not
exact.
exact,
There's
but-
uncertainty in all these. Okay, but we have 0 decimals. How many decimals are we allowed here? 0. So this is where I really would, to me, you can't carry it through because it creates uncertainty. So that's the calculator. So what's my answer with 0 decimals?
5.
Since this is a 7, what are we going to do with the 5?
6.
Exactly. Stepwise, don't blame me, right? So now I'm going to take my 6 divided by 79. Okay? Somebody say what the calculator displays.
0.075949367.
0.0759.
49367.
Okay, that's fine. Thank you. So I'm going to put calc there, okay? All right. So do we count decimals or sig figs?
Sig figs.
We count significant figures. How many significant figures in 6?
One.
Just one. Only one. How many significant figures in 79?
2.
2. It's a little game we played. So how many significant figures am I allowed?
2.
One.
How many people think 1?
Oh, 1. Yeah.
Yep, me too. All right, so here we go. Okay, we keep the first, only one, non-zero digit. So actually, I'm going to have to go ahead and put 0.0. And I'm going to keep this one, but I'm going to truncate it right there. This is a good example. So since that is a 5, what am I going to do with the 7? I'm going to round it up, exactly. So your answer to this mess is 0.08, and of course, whatever units. Okay? And I'll go ahead and take a snapshot of this and throw it up there on the Twitter feed. But any questions?
So basically, whatever we do last is whatever rule we carry over. So if it's adding that we do last, then we'll follow the decimal points. And if it's
Yeah, but to me, to get to that point,
Yeah.
though, oh, I think I see what you're saying.
yeah,
Mm-hmm.
Or-
Yeah, if you wanted to keep
Oh,
the best
okay.
value possible.
Yeah, okay.
But I generally don't. I generally discourage keeping the unrounded values, quite frankly. Even though they give you a better number, I've seen it come out bad too many times. Okay, so I would round. Don't go for the gold. But maybe.
maybe.
Okay, so I want to do the first 9 slides of this. We won't get to another assignment slide, but getting into this property of how fluffy or how dense something is, okay, is going to help us tomorrow. We'll have less blah, blah, blah tomorrow. How's that? for encouraging. So, density. Density. You probably already have an idea of how dense, the whole density thing. I have a picture coming up of somebody holding styrofoam and somebody holding a rock. Which is more dense, styrofoam or the rock? The rock seems more dense. If that would be what comes to mind first, that's right. The rock is more dense. The styrofoam is more fluffy. Basically, the mass in the styrofoam is less, okay, than the mass in the same volume of the rock. The mass, the thing about the rock is it's all packed together. Okay, does that make sense? So density is basically a division problem, and you'll be doing that tomorrow. Okay, can you kind of see the division? Division problems are kind of masqueraded by the word ratio in physical science. Okay, so don't let that throw you off. Anytime you see ratio, think division. Okay? So in order to get to the density of something, we have to get a fix on a certain chunk of matter, and we have to get the mass of that matter and the volume of that matter. Throw it in our calculator, we get the density of that chunk of matter. So we talked about the physical phases of matter, excluding plasma. And so matter can either be a solid, liquid, or gas. Which one of those has the most kinetic energy? How many people think it's a solid? How many people think it's a gas? Me too. Cool. Along those lines, then, here's another one. So which one of these will go ahead and take whatever volume you give it? How many people think solid? How many people think gas? You're right, exactly. So gas is already kind of your wild children, okay? So the other thing, though, aside from, how do I say this? If you have a box of gas, and if you cool that box of gas down, and you're going to keep it the same pressure, that's assuming you're going to keep it the same pressure, what will happen is basically when you cool it down, it will occupy a smaller and smaller volume at the same pressure. Okay, it just does. Why do you think that would be? If you cool it down, what happens to its energy? Slows it, yeah. I love gases because you're like, oh, that makes sense. I can relate to that. Okay? Okay, so gases are really, the volume that a gas will occupy is really temperature dependent. Liquids a little bit. When you take liquid water and you cool it down, it does shrink too. Liquid water gets smaller, okay? If you take water that's already solidified, Okay, it's already ice, and you make it small, cool it down. Okay, to a lesser extent, it will get smaller. Okay, volume. I qualified that because there is the transition when water goes from a liquid to a solid. That transition point, they're about 0 Celsius, 32 degrees Fahrenheit, it fluffs out. And there's a reason for that, and actually we're going to talk about that on Wednesday more. But if it's a liquid, you know, water will be fluffier at 10 degrees Celsius than it is at 15. Wait, I said that wrong. At 20 degrees Celsius than it is at 15. It'll be fluffier at 20 and more compact at 15. Okay. Oh, darn it. I already showed you the answer. What type of property is density? How many people think, so your choices are chemical or physical. How many people think density is chemical? How many people think density is physical? Why do you think it's physical?
Because the answer says.
What's the other reason you think it's a physical property? Do you have to do any sort of chemistry? No? Any chemical reactions? No. You might have to get out the balances, but when you put something on the balances, it's getting data, but is it chemical reaction?
No. It's just weighing it.
Right. Here's one for you. The other question says intensive or extensive. Intensive means independent of amount. Independent of amount.
So it's extensive.
Extensive.
Actually, it
Well, I
is
mean-
intensive. And I'll tell you why.
Because it's a ratio.
Yes, because it's a ratio. The weird thing about it is we definitely know mass is extensive and volume is extensive. Mass and volume clearly depends upon how much you're weighing or how much you're getting the volume of. Okay, so those are extensive. But the fact that, for instance, water has a particular density at 15 degrees Celsius, liquid water. Okay, what if you have a cup of that or a chilly bathtub full of liquid water at 15 degrees Celsius? It still has the same density. Yeah.
Because it's still
So-
water.
Yeah, it's still water at that temperature, exactly. So it's intensive. Okay. So in this class, it's about numbers. Okay, we have kind of, to me, almost two aspects of chemistry. And it's funny because chemistry, there's something called organic chemistry that you would take after general chemistry. And then this is general chemistry. This is like inorganic or organic, and they almost have two brains. Okay, organic chemistry is about the pretty part, how molecules connect and why they connect and kind of the mechanism. Organic chemistry is a little more like biology, you know. But we have a lot of numbers in general chemistry, and just regular chemistry. Which each number we have units. So I told you that density is a ratio of mass to volume. Oh, I didn't emphasize this. And tomorrow, like I said, you're going to be coming up with some densities. But as I walk around, I'm going to be looking for that. It looks like the P, but that is the Greek letter. Is it? I don't think it's spelled. How do you spell rho? I don't think it's R-O-W. But anyway, this is a Greek letter, okay? And that's just the symbol for density. It's a small thing, but I will not allow you to use a capital D in here for density. Just me. Greek letter rho, okay? Symbol for density. So when we do density, like you saw on the previous slide, it's a ratio. We take the mass of an object and the volume of an object and do a division. There are units associated with mass, and here down here, the possible units of density, you see in each case, we're going to go with grams. But there are an assortment of ways of describing, and tomorrow you're going to have volume in terms of milliliters and also centimeters cubed are great practical ways of saying volume. Okay. So of these ways of expressing the units for density, this is probably what I call kind of the unpacked version of grams per mil. Did you guys know anytime you hear the word per, basically that's like a little divisor? Okay, what's your mileage? Oh, I drive a cube, and if I'm doing good, it gets about 30 miles per gallon. So per is always like a little divisor. Okay. This one right here, this one is the flattened out one. But do you see where they're the same thing? Okay. And again, this third one here basically says instead of milliliters per volume, I'm going to go with centimeters cubed. Remember how that works is to get the volume of anything that's maybe got, you know that it's boxy? Okay, you can take the length and the height and the width of that box times each other. One more thing down here then is anytime, and I don't do a lot with it in this class, but anytime you see something like units, like milliliters or centimeters cubed raised to a negative power, that automatically means that thing is in the denominator. Okay, I think we talked the other day about numerator north, denominator down. Anything that's raised to a negative power is in the denominator. This just happens to be raised to the negative first, so it's in the denominator, the first power. Okay, centimeters cubed, quantity raised to the negative first power. In the bottom, raised to the first power. That's all that means. All right, so let's work a problem. So like I said, what you'll be doing are taking a couple of objects, the block of color of your choice. The other object will be a black stopper. Everybody gets the same color. And those two objects, you're going to, one way or the other, well, to get their mass, you're just going to throw them on the balance, right? To get the volume of the block, you're going to go ahead and get the dimensions of it and multiply those three unique dimensions together to get the volume. To get the volume of the rubber stopper, it's going to be what I call the Crisco method by displacement. So before Crisco came in sticks, we used to have to basically, if we wanted 1 cup of Crisco, we'd have a 2-cup measuring device. We'd put cold water up to 1 cup and blob in, not mine, blob in Crisco until it went up to displaced water to 2. Okay, and then we're going to do the division. That's step number 2 there.
Nope.
I think it's mine. Okay. This last one, I'm going to put a question mark next to it. Okay. This last one, I'm not so sure. This morning I was looking at it, and you know what? As long as you have units of mass to volume, I'm like, you really don't have to go ahead and get the mass to grams and the volume to either milliliters or centimeters cubed. I'm kind of debatable about that. I'm arguing with myself on my sides. So let's work a problem. I mentioned tomorrow you're going to have a block that you're going to get the 3 unique dimensions of. Okay, so instead of metal alloy, it's going to be wooden. But you're going to come up with the dimensions. And then you're going to have, you're going to use the scales to get the mass. So they already did this for you. Let me get my calculator handy. Okay. So we talked about kind of doing things stepwise. You're always going to show your work. So in your tomorrow, bless you. Tomorrow I will be looking for you to go ahead and write all 3 dimensions together. And I really kind of like getting in the habit of things you need to multiply together to get the volume, these lengths to get the volume. Go ahead and put them in parentheses. Okay. And then remember we talked about when we did area, you kind of consider taking the numbers times each other and taking the units times each other. So I'm going to go ahead and do this one. You guys can too. Okay. So I had a slide that said, go ahead and round your intermediate numbers. Okay. So did your calculator, and like I said, this time I went ahead, I bet your calculator displayed 1.76358? Good. 1.76358. Since we're multiplying these 3 numbers, we're going to go with sig figs or decimals?
Sig figs.
Yep, sig figs. So counting sig figs from left to right, how many sig figs in this first term? 3. How many sig figs in this next term? 3. Everybody agree? How many sig figs in 0.76? 2. Very good. So do you see why, starting from left to right, we're going to keep 2 sig figs, the 1, the 7. Okay, we're going to drop it right there, okay, at the 10th place. And since that's a 6, we round up the 7. Does that make sense? Okay. So now what are we gonna do to finish off density?
It's rounded to 1.8, and then it's, since you have 3 centimeters, it's gonna be centimeters cubed.
Right, centimeters cubed. And then how do we, density is a ratio of what to what? What's our division thing?
To volume.
Grams to volume, exactly. So then we just go ahead and put those in there. Okay. $13.94 divided by, and this is where my slide is different. I'm just gonna, you guys are doing it too, but I bet you guys got 7.74 repeating. Yeah, I love repeating numbers, right? I say I'll qualify it as calculator displays 7.74444. Cool. Yeah, with a line over the 4, right? So how many significant figures in the mass? 4, I agree. How many significant figures in the volume?
2.
Only 2. So how do we need to round this? I kind of asked a weird question. I heard somebody say 2, and I heard somebody say at the 7, and you're both right. Does that work? Okay, good. So we would report our number as 7.7. Does that seem right?
Grams per centimeter cubed.
Thank you. No naked numbers. 7.7 grams per centimeter cubed. Perfect. Now, why does this say 7.9 grams per centimeter cubed? If we use
Because the density is in or in grams, and the, or not the density, but the volume is in.
could be.
grams.
I
The
kind of
volume's in
set you up. By the way, 7.7, awesome answer. You get smiley face, check mark. The thing I did to get this was to use the unrounded value, 7.74 repeating. Okay, if you basically, oh, that wasn't right. The unrounded value of the mass, 1.76358.
Ah.
You know, and we talked about that a minute ago. So I would take either answer. Like, really? I'm like, yes. Okay, but this is using the unrounded. Okay?
You're supposed to round it, right?
I would encourage you to round it, but if you don't round it, this is fine too.
Maybe a really silly question, but where did you get the 13.94 grams from?
That was from the slide before, that somebody went to the scale, did it for us.
Thank you, I'm sorry.
You're fine. All right. Let me know that. We'll have more examples where it's rounded or unrounded. See you tomorrow.
Yay.
Yes.